Okay, class, welcome back to Math 7. This is Chapter 8-5b. We're going to be learning about two kinds of numbers that we do talk about in math. Now, you are used to working with some of these you are not. You are used to working with rational numbers. You have worked with them off and on since you were very young. A rational number, according to definition, can be written in a fraction form of a over b. Now, the a and the b have to be integers, and b can never be 0. That denominator cannot be 0. If you try to put an integer over 0, we call that an undefined quantity or an undefined concept. What are some examples of rational numbers? We have several. We have whole numbers. Now, these are the numbers that you started working with way back when you first started in school. They're numbers like 0, 1, 2, 3, etc. They're counting type numbers. You are also used to working with integers. You started working with them just a couple of years ago. Integers, if you recall, are what we call directed numbers or signed numbers. They would be numbers like 4 or -4, maybe a -7, a 5, etc. So they're your positive and negative numbers. You've also worked with terminating decimals. Some examples would be 0.14, 0.5, negative 0.875, negative 0.3, etc. You have worked with those too, and this year we did start working with those in an earlier chapter. Now notice that terminating, maybe that's a word you don't know, but to terminate means to end or to stop. Terminating means that it's a decimal that has a definite stopping place. It terminates, it ends, it stops. It doesn't go on forever and ever and ever. Another example of rational numbers are going to be our fractions and mixed numbers. So some examples here would be 3/4, -7/8, 1 1/3, that's a mixed number, -7/3, so notice that you can have improper fractions, -1 1/2, and I think you get the idea. Well, what about repeating decimals? Yes, those are also going to be examples of rational numbers. These two you've worked with before. 0.3 repeating. Sometimes they don't write them with bar notation. They'll have the pattern established, and then they'll use 3 dots. In English, it should be all in a row. In English, we call that an ellipsis, but that's a designation that means, and that's the way it continues, or and so on. We have also worked with the negative ones to some degree, so you can have a -0.6. Don't forget that sometimes you can have a 0.012 and only have the 1, 2 repeating. So that is also a repeating decimal. And of course, any other numbers like that. There's one more, and those are the square roots of the perfect squares, which we just got done working with in our prior lesson. So we can take 49. The square root of 49 is going to be a perfect square, and is going to be a rational number, because that's a 7. The square root of 900, which is 30. Well, 30 is a whole number, so of course that's going to be a rational number. And remember, we had some of these the other day in the lesson. The square root of 16/25 is going to be 4/5. Well, that's a fraction, and a fraction is a rational number. Well, what about irrational numbers? Well, they're the ones that can't be written as a ratio of integers. What are some examples there? We have non-terminating and non-repeating decimals. you will have decimals like 0.3232, 3222, etc., etc., etc. Now notice that's not a repeating decimal because the pattern does not repeat precisely. First it's 3 followed by 1 2, then it's followed by a 3 and 2 2s, etc. Here's the number pi. Pi is like the classic example of the irrational number. It's actually a non-terminating, non-repeating decimal. We simply use it as an estimation at 3.14 or 3.1416. That's why I think sometimes students don't think it's irrational, but it really is. Because in reality, pi never ends. It does not end. And it does not repeat. And you can also have the negative idea. So you can have negative 1, 2, 1, 2, 2, 1, 2, 2, 2, dot, 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 etc. We don't have that many examples of irrational numbers. The only one we really have is b, the square roots of numbers that are not perfect squares. What do you mean, Miss Scouten? Well, we mean things like the square root of 2. If you actually took your calculator and put square root of 2 in as a problem, it would actually keep going forever and ever. Now, even on your calculator, it's going to stop at some point because your calculator only has a certain number of characters that it will show you. In reality, this number, the square root of 2, just like pi, would go on and on and on and on and on to infinity without ever repeating. Another one, of course, would be something like the square root of 14, and so on. Now, remember to use your list of perfect squares that I gave you in your notes when you are working on the assignment, because maybe you don't recognize whether or not the number is a perfect square, especially if it's one of the bigger perfect squares, like say 169. You might not know that one right offhand. So therefore, make sure that you have access to that paper that I gave you on perfect squares the other day. Okay, now, what am I going to have to do for an assignment? One of the things you're going to have to do is identify whether a number is rational or irrational, and then you're going to have to explain or tell me why. Now, how do I do that? I'm going to be using these types of things here, that the number is a whole number, that the number is a terminating decimal, or if it's irrational, that it's a non-terminating, non-repeating decimal, that it's a square root of a number that's not a perfect square. So let's look at some examples. Square root of 15. Well, check your perfect square list. Is it on there? Nope, it's not. Therefore, we are taking the square root of a number that is not a perfect square. So the number itself, the square root of 15, is a number. It has to be irrational. Our reasoning, our explanation, is that 15 is not a perfect square. Okay, look at B. What do you think? Is it going to be rational or irrational? You're right, it's rational. Why? 100 is a perfect square. Okay, check out C. 0.42142214222221. What do you think? Rational or irrational? Check through the lists that I showed you for examples of rational numbers. Does it fit any of those? Now check the list of the two things for irrational numbers. Does it fit any of those? Yes, it's going to be irrational. And our reasoning is that the decimal does not terminate, nor repeat. Wow, we get to write some long explanations. Yes, we do sometimes. Let's look at D. Stop. Think it over. If you have to, hit pause. Look at your things. Look at your reasons that I gave you for rational, your examples I gave you of irrational. What do you think? Yes, it is rational. And our reason is that it is a terminating decimal. Okay, check out E. Yes, it is rational. Why? Because it's a repeating decimal, even though they didn't use the repeat bar, otherwise known as bar notation. Remember, I gave you an example in part 1 of the notes that you can show repeating decimals by using just the pattern and then the ellipsis. That concludes lesson 8.5b. Please respond with the word pentagon. Catch you next time.